So in this screencast, we're continuing to investigate nucleophilic substitution reactions. And so when we think about a nucleophilic substitution reaction, and we look at the reaction here where we have reactants and products, what we're seeing is that the bond here with the alkyl halide, that sigma bond is broken, and a new sigma bond forms with a nucleophile. Now, the question that we ask as scientists is, what's the order of bond making and bond breaking? And in theory, there are three possibilities. Bond making and breaking could occur at the same time. This would be that concerted reaction, which we've already talked about. The other thing is that bond breaking could occur first, or bond making could occur first. And so we use experimental data to determine which of these things is happening. And so we're going to talk about that throughout this screencast as well. So we're going to look at two scenarios here, two possibilities. The first possibility is that bond making and breaking occur at the same time. This would be an example of a concerted reaction. So for example, if we have our alkyl halide here and our nucleophile, which is going to be negatively charged or have a lone pair of neutral with a lone pair of electrons, right? We look here and we say, okay, there's our halogen, and we know that that is very electronegative. It's going to withdraw that electron density. And then we are going to come over here. We know that that makes that carbon partially positive. So the nucleophile then will come in and it will attack that carbon right there. Now, this produces for us, when we follow those arrows, the nucleophile attached, and then our halogen, right, leaves. We have our leaving group here, which we're using a halogen for, and it carries that negative charge. This forms a carbon nucleophile bond. Now, this is shown as one step. So this is a one-step mechanism, okay? And it is referred to as a bimolecular reaction. So the prefix bi means two. And the reason it's referred to that is because these two reactants have to collide, okay, for this reaction to occur. So in a bimolecular reaction, what that means is that the rate depends on both, let's say, the concentration. So of the concentration of both reactants. So what this means then is that this reaction is second order, right? Because ideally, or what we see is, the rate equals the rate constant times the concentration of the nucleophile times the concentration of the alkyl halide. Okay, so this will be a second order reaction. Now, if the bond breaking occurs before the bond making, then we end up with a two-step reaction. So let's look at this mechanism. So what we see here is that this bond is broken first, then a carbocation forms, and the nucleophile comes in and attacks that carbocation. We've got a negative and positive, okay? And so then the carbon nucleophile sigma bond is formed. This mechanism is a two-step mechanism, okay? And the carbocation is formed as an intermediate. right? And the first step is the rate determining step. Right? So this means that then the rate would just equal, right, the rate constant times the concentration of the alkyl halide. The concentration of the nucleophile does not affect the rate. And so this also means that this rate equation, or this rate, is first order. Okay? So we use the data from the rates to help us figure out which mechanism is occurring. If we are studying a mechanism and we double the concentration of the nucleophile and it doesn't affect the rate, then it occurs through this mechanism. If we double the concentration of the nucleophile, then, and it does affect the rate, then it occurs through the previous mechanism, that concerted mechanism that we talked about. So let's look at this reaction here. So let's say we walk into the lab and we are studying the kinetics, right? And we double the concentration of this and we see that the rate doubles, right? And we double the concentration of this and we see that the rate doubles. This suggests that this reaction, right, occurs by these two things colliding with each other, right? And so that suggests it's a bimolecular reaction with a one-step mechanism. Now, this is an example of what we call a substitution nucleophilic bimolecular mechanism. Now, like all good scientists, we're going to shorten this name to just SN2. That's it. Because we have two molecules that collide, that's where the 2 comes from, okay? So that is shortened. Now, we are going to spend a lot of the rest of this screencast talking about SN2 reactions. One of the things that I want you to know here is that it is a one-step mechanism. Now, maybe the burning question in your heart is, hey, Dr. Pierce, what happens if it's first-order kinetics here? Well, if it's first-order kinetics, which is what we see here, then the rate only depends on the concentration of the alkyl halide, right? The nucleophile doesn't matter. It just depends on the concentration of that particular species. And so that then suggests that this is a substitution nucleophilic unimolecular mechanism. And again, like all good scientists, we shorten this to an SN1. Now, when we talk about an SN1 reaction, it depends on just one molecule here. That's where the 1 comes from. But you need to remember, this is a 2-step mechanism, right? And it only involves the alkyl halide. Now, we are going to look and really dig into SN1 reactions in the next screencast. And so the rest of this screencast, we're going to talk about the SN2 reaction mechanism and some other information besides just rates that can help us differentiate between SN1 and SN2. So when we talk about an SN2 reaction mechanism, okay, this is how we would draw it. If we were to start with, for example, this guy here, and this guy here. And we were asked to draw the mechanism and predict the products. That's the example, right? It's the problem we've got. Draw the mechanism and predict the products. What we need to do is we need to say, okay, hey, look, this is the nucleophile. We can identify the nucleophile because it's carrying a negative charge here. Then we need to come over here and we say, look, we know this is an alkyl halide. And that means that this bromine is electronegative, which makes this carbon partially positive. So what that means is the nucleophile with that oxygen that has all that negative electron density is going to come over here and it's going to attack that partially positive carbon because positives and negatives are attracted to each other, just like magnets. Then when that happens, it's going to break the bond between the carbon and the bromine, and those electrons are going to go and hang out on that bromine. So we follow the arrows because this tells us electron movement. It's saying, hey, look, these electrons are going to form a new bond with this carbon. So when we start to write the products, we write everything that doesn't have an arrow involved in it. Then when we get to the oxygen, we see there's an arrow here, and that arrow says, look, those electrons form this new CH3 bond. Then we say, all right, we get here, and oh, this arrow is showing that those electrons are going on the bromine, and this is the bond that breaks. So that gives us a second product here, which is bromine. Okay, so the arrows are really to help you figure out what bonds are forming and what bonds are breaking. Now, if you were asked to write the rate equation, then you would take the rate and you would say, look, the rate equals K times the concentration, and you can specifically put in here the alkyl halide and then the nucleophile, like that. Okay, so that's the specific rate equation for this reaction. Now, when we look at the transition state here, what we would see is that we have this oxygen, and then what we would do is we would draw a dashed line where we have an arrow, and we would say, look, we have a carbon here, and that carbon has 3 hydrogens on it. We're going to draw it like that. And that dashed line shows the bond that's forming. Then we would also show the bond that's breaking here to the bromine. Now, because the oxygen has a negative charge, we would say that's partially negative. Because the bromine ends up with a negative charge, we would say that's partially negative as well. And so we would put brackets around this because it's the transition state. And then we would use the double arrow there. So this transition state shows that the carbon-bromine bond is partially broken and the carbon-oxygen bond is partially formed, right? And it shows both the attacking nucleophile and the parting leaving group have that partial negative charge. Now, let's talk about stereochemistry, which can also give us information about the mechanism. So, when we talk about stereochemistry, there are 2 possible directions where the nucleophile can approach the substrate. The first is called a front side attack, and this is just when the nucleophile approaches from the same side as the leaving group. Then you can have, and so let me show you this, right? We have a nucleophile here. There's the leaving group there. There's that halogen of the alkyl halide. This can come in here and attack that partially positive carbon, and the bromine can leave this way. That's a front side attack. If the nucleophile attacks from the opposite side as the halogen, that's called a backside attack, which is shown here. Now, so a backside attack is where the nucleophile approaches from the backside. I'm going to say from the side opposite so that I'm not using the same word in the definition. Side opposite the leaving group. Right? So this affects stereochemistry. If you have a front side attack, what happens here is that the product retains the stereochemistry. So what does that mean, right? Well, if this starts as R, this will also be R. If this starts as S, this will also be S. That is not the case with a backside attack. With a backside attack, the stereochemistry is inverted, right? And so this is called this process is called the inversion of configuration. And what does that mean? Well, if we start here and this is R, then we're going to end up with S and vice versa. So the product here ends up being a different configuration than the starting material. Now, that only, of course, happens if you start with something that is an enantiomer. Okay, so if you start with the enantiomer S, it ends up being the enantiomer R. So I want us to look at this transition state and some examples. So when we look at the transition state, which we've looked at with a specific example, this is a more broad sample. When the nucleophile comes in and attacks through a backside attack, we see that the nucleophile is here and the bromine is here, right? And we see these partial positive charges. What we see is that the nucleophile and the bromine are always kind of 180 degrees from each other. And I like this image here because I feel like it really shows that inversion of configuration, right? Where you start out with one enantiomer and you end up with a different enantiomer. So if we look at two then specific examples, right, we have two specific examples here. And so I want you to notice, right, this is an example of a backside attack. It comes in and attacks on the opposite side from the halogen, and we end up with a different configuration than we do here. Same thing occurs here, right, where this OH comes in from the opposite side of the halogen. This halogen leaves, and we end up with a different configuration here than we had here. So the big thing that we notice here is the bond to the nucleophile in the product, here and here, is always on the opposite side compared to the bond of the leaving group in the starting material. So, for example, if we have the iodine here as the leaving group, then we see the thiol ends up on the opposite one. These are both in the plane of the paper, okay? If it's on a wedge, for example, then what we see is that the nucleophile will end up on the opposite wedge. So if the halogen was on the solid wedge and the nucleophile comes in opposite of it, the nucleophile ends up on the dashed wedge. So I like this because it shows you how to show that stereochemistry and that inversion when you have groups that are on the same plane as the paper, as well as when you have groups that are on coming out of the paper here. Okay, so really a great example there of how to show that stereochemistry. Now, maybe the burning question in your heart is, Dr. Pierce, with this backside attack, that seems like sterics would really affect this reaction. And you would be correct. So let's talk about sterics for a moment. When we talk about sterics, right, what we find is that as the number of R groups on the carbon with the leaving group increases, right, the rate of an SN2 reaction decreases, okay? And so what does that mean? Well, when we look here at our classifications, we can have a tertiary halogen, a secondary halogen, and a primary halogen, and then a methyl halogen. And what we find is that this is going to be when we compare these in a reaction, we find that methyl is going to be the fastest, right? And we find over here that if the substrate's tertiary compared to that methyl, that's going to be the slowest, okay? And so what we find here is that with increasing steric hindrance, as you add more groups to the carbon next to the halogen, we find that the reactivity will decrease. So when you increase steric hindrance, we decrease activity. Another way to say this is, right, as we decrease steric hindrance, we increase the activity here. And so remember, if it's increasing this way, then it's going to be decreasing this way. So what does that mean for us? Well, methyl and primary alkyl halides undergo SN2 reactions with no problem, right? Super easy. Secondary alkyl halides are very slow, and some older texts will say that they don't react at all, but there have been some papers that have shown that secondary alkyl halides do react. It's just incredibly slow. Tertiary alkyl halides are so slow that we just say they do not react. So we say they don't undergo SN2 reactions due to steric hindrance, right? And so those bulky R groups next to the reaction site make this nucleophilic attack from the backside really difficult, and it slows the reaction rate down so much that we really don't see any product here when we do this reaction. Now, I love good summaries. This is a beautiful summary here of SN2 mechanisms. So when we have an SN2 mechanism, the kinetics are second order kinetics, and that's a generic rate law. And we did an example of a specific rate law in this screencast as well. This mechanism is a one-step mechanism. The stereochemistry, the mechanism occurs through this backside attack, which results in an inversion of the configuration at the center, which means if we start with R, then we're going to end up with S. And then when we talk about the identity of R, right, what we find is that steric hindrance matters. So unhindered halides react faster. So that means that your methyl halides are going to react much faster than your tertiary ones. So sometimes the greater than or equal than to throw me off, right? And so I just always like to define these as fast and then slow. Now, I love a good practical application. SN2 synthesis is used in the synthesis of drugs. Here are two really great examples where we end up with an SN2 synthesis. This SN2 synthesis is really interesting. It'll attack here to attach and form that bond. And then a second equivalent of that molecule will come in and attack here to form the bond there. This is a sequential reaction, right, where we see the amine group being substituted for the iodine. And then what we find is that there's another reaction here that we haven't talked about yet. but this is one step in the synthesis of Prozac. So this is used in the synthesis of drugs, which again, I find to be really interesting. In the next screencast, we are going to talk more in depth about the SN1 reaction. If you have any questions, as always, please feel free to stop by my office.